In this chapter, we're going to be talking about ARIMA models. ARIMA models are very popular approaches to time series forecasting, just as exponential models. While exponential models are usually trying to describe the trend and the seasonal components that are present in the data or in your time series, ARIMA models typically describe or build on models using the autocorrelations that are present in the data. Now, the outline of our chapter is going to be the following. We are going to be talking about something that's very fundamental to working with ARIMA models, which is making your time series stationary and the technique of differencing. We'll proceed with looking at non-seasonal ARIMA models, and later on we'll talk about seasonal ARIMA models. We'll talk a little bit about the estimation and order selection for our models, and then how do we translate these models into in an applied setting in R. And last but not the least, we will forecast the models. Okay, like the tail end of the chapter is going to be talking about some of the differences and similarities between ARIMA and exponential smoothing methods or models. Now let's talk about stationarity and differencing. We have discussed this at length in class, but stationarity by definition for a time series is as follows. If yt is a stationary time series, then for all s, the distribution of yt through yt plus s does not depend on t. In other words, to make it non-technical, in other words, the properties of the time series don't depend on the time that the series is observed. So at any point in time, if you observe the time series, it should look just about the same. So a stationary time series, again in non-technical terms, is roughly horizontal. It should display constant variance, so it should not show you periods of very high volatility versus periods of very low volatility. It should display sort of its constant variability over time, and there should not be any predictable patterns that are observable in the long term. Now we can take a look at different types of time series, and here's one, which is the Google closing stock price for the between 2018 and this is for the entire year of 2018. And if we notice this, this does not look stationary, because we can take a look at, let's say, the first half of 2018, and that looks very different than the last half of 2018, and even the mid 2018 is very different, where the stock price is climbing up. So it definitely is showing a trend here, okay, with slight ups and downs. But this definitely does not look like a stationary time series. But if we take a look at the daily change in the same series, so we call this the difference series. Now we're looking at what is the change from one day to the next. This series is going to look a lot different. It would look like it's roughly horizontal, right? It's not climbing up or down. And there are some periods of changed variability over time. So this period right here looks pretty volatile, and this period here looks very volatile, versus these periods, they don't look as volatile. So maybe this is stationary, maybe not, but there are sophisticated tests that we can use to understand whether the Google stock price daily change is stationary or not. Now this is the number of strikes in the United States, and this is annual data over time, so this is very old, and this doesn't look like a stationary time series, again, for the same reasons as we described. This is data that is looking at the sales of new 1 family homes in the United States, total sales over time. Definitely what you see here is marked seasonality, very strong seasonal patterns that exist within the year. So again, the data does not look stationary. This is a data set that is looking at the price of a dozen eggs in 1993 dollars, and take a look at how crazy the price of eggs was here. And obviously, this has come down substantially, in recent years. So again, this is showing you a trend. This definitely does not look like a stationary time series. Okay, this is showing you the number of pigs slaughtered in Victoria, in Australia, the state of Victoria in Australia. Again, this is not displaying stationarity because this is showing you some sort of seasonal patterns that continue to persist over time. Finally, you have this data set that is looking at annual Canadian lynx trappings, the number of lynx that are trapped in Canada, and maybe what you see here is sort of a roughly horizontal series with these ups and downs that are displaying very rigid cycles. But actually, sophisticated tests would reveal that the cycles are actually aperiodic, and the lynx population sort of fluctuates, rises and falls based on the available food that's out there, and that causes the fluctuations in the population and the trappings, therefore. Finally, we have Australian quarterly beer production, which is showing you a very, very strong seasonal pattern. So again, this is not stationary. So just to wrap up here, again, stationarity is defined as a series that is roughly horizontal over time. It does not show change in variability, and there are no predictable patterns that are there in the data. And ARIMA models would use stationarity and run with that type of an assumption on the data. So we have to make our data set stationary before we can apply ARIMA models on it. Okay. So how can we make the data stationary? There are some transformations that we had talked about earlier, the Box-Cox transformations that can help to stabilize the variance, for example, taking the log of the time series or using some kind of power function. But for ARIMA models, we also need to stabilize the mean of the time series, so some kind of an unconditional mean that you see in the time series. Now, whenever you're eyeballing the data, you're graphing the data and trying to make a judgment on it, whether it's stationary or non-stationary, some of the useful things you can do are to identify non-stationarity are to look at a time plot and then take a quickly look at the autocorrelation function of the time series. So if the data are stationary, the autocorrelation function of stationary data would drop to 0 relatively quickly. So there is this decay that you would see over time. But if the data are non-stationary, then the data is not going to decay to 0 very quickly. So you're going to see this very, very slow decay over time. And you'll be able to see that in an example shortly. So if you have non-stationary data, the values of your autocorrelations over time for different lags are quite large and positive. So let's take a look at the Google stock price again. This is the Google stock price. We'd seen this chart for 2018 earlier. And let's take a look at the autocorrelation function here. So you see these large values of the autocorrelations for different lags, and it doesn't seem to decay to 0. You can even extend the lags and see that it takes a long time for the autocorrelation function for this type of data to decay to 0. And so this is a characteristic of non-stationary data. However, if we look at the daily changes in the Google stock price, then the data looks sort of horizontal with different variability over time. But if we look at the autocorrelation function of that data, then it would look or really resemble a white noise process. Which would mean if it is a white noise process, that we really can't use any type of linear model on it and forecast the time series. Okay. So in the next video, we'll talk about differencing.